So thanks for the opportunity for letting me explain what I have been doing here the last several years. But before that, I want to start with telling you a little bit about my background. I have been studying fluorescence for my entire career, and in the beginning, it was mainly on more classical fluorophores, more organic dyes. But around the end of my PhD, I came across some work from Robert Dixon, who you can see here, and also Jeff Petty, who is a regular visitor here in Copenhagen, who basically published this landmark paper in 2004 about fluorescence from silver nanoclusters, and I was quite intrigued by that. So I did my postdoc in the group of Robert Dixon in 2005 and 2006. And yeah, so why is it, or how can we sort of conceptually understand that small silver clusters can be fluorescent? Well, if we go from the atom to the sort of bulk metal level, then the properties can change quite drastically. So at the bulk level, um, for example, silver, it will have sort of conduction and valence bands, while at the atomic level, you will have atomic orbitals. So somewhere in the middle, we can make clusters which have sort of molecular-like properties. And just like organic fluorophores, we can sort of excite these small metal clusters and then they can fluoresce. Now, the tricky part is that we have to prevent these small clusters from aggregating into larger nanoparticles or into bulk metal. So the easiest way to do that is by using a ligand or a scaffold in order to tune the size and the charge and the shape of the particle. Now, people have used many different types of ligands. You can use peptides, polymers, zeolites, and also DNA. It just turns out that DNA is a quite suitable scaffold in order to control the size and the shape and the charge of these silver nanoclusters. As you can see here in this diagram, by basically just changing the DNA sequence, we can change the type of cluster that is stabilized. This is also exemplified here. So while most of you probably know that DNA stores the genetic information that allows living organisms to make proteins or encodes this information in the DNA sequence. Similarly, we can also say that by changing the DNA sequence, we can sort of have a specific cluster being stabilized. And this arrow that I indicate here is sort of what we have been working on, trying to unravel how it is that a certain DNA sequence is good at stabilizing certain silver nanoclusters. Now, the first thing to know is that silver really likes to bind to DNA, and it can, as I shown here, can even disrupt the classical Watson-Crick base pair interactions. So here you can see an example from my collaborator Jiro Kondo, who has published this nice study where you can see that the silver can, for example, remove the proton here and take over its place and make a silver-mediated base pair interaction. Additionally, silver can also make mismatches. For example, here we can see that we can bind a G with a G and a T with a T. He had this very nice structure where he made a one-dimensional array of silver-mediated base pair interactions up to micrometers long. So it shows you that silver can really likes to bind to DNA and to nucleobases. And how do we make then small clusters? Well, the only thing we need to do is then add a reducing agent to reduce some of these cations to silver zero. And that's usually what we do. So we usually buy DNA, add silver nitrate, and then we reduce it with some sodium borhydride. And this workflow is also given here on this slide. So we mix the three things together. Then we wait a while, depending on the sequence. Then we wait a couple of days, and depending on the sequence, it can be one or several days. Usually we follow that with absorption and fluorescence to see at which point we have achieved our maximum yield. And then after that, we do HPLC purification in order to get our specific cluster of interest. So then we end up with atomically precise DNA stabilized silver nanoclusters. And this is quite important because that also allows us then to get really the intrinsic properties of these emitters. If you don't do the purification, you just end up with a soup, and yeah, the values you get out are not so representative for the individual cluster. Now, the fact that we HPLC purify them also allows us then to do mass spec and to determine sort of the composition of these individual atomically precise emitters. So I have given here one example of such cluster. This is a silver 16 cluster, which also has two chlorides. And mass spec also allows us then to determine the charge of these emitters. As you can see here from the figures, there's only one charge that really matches very well to the isotopic pattern of our atomically precise cluster. So I have indicated here also silver is roughly 50-50, silver 107 and silver 109. And as a result of that, you will see this isotopic pattern even for a single species. And that allows us to determine what is the charge of the cluster. Now, to give some examples, here we have two sequences, and you can see that they give or stabilize fluorophores with typical molecular-like properties. For example, we have here two emitters with excited state lifetimes of a few nanoseconds with reasonably high fluorescent quantum yields. And as you can see also, usually they have relatively large Stokes shifts. And very often the absorption spectrum looks like given here. We have one main peak at 260 nanometer, which is related to the DNA absorption. And then we have usually one peak further in the visible range that is related to the silver nanocluster related transition. Okay, and then a couple of years ago, we actually showed that these clusters are very good, and they keep their high brightness even in the near infrared region. And here we wanted to highlight this by doing single molecule measurements of this particular cluster. That was a silver 30 cluster that emitted around 950 nanometers. And we showed that we could do single molecule measurements and even show that by using fluorescence anti-bunching measurements, we demonstrated that these are single emitters and not aggregates of clusters. So the idea here is that they show that they have quite high potential to be bright emitters in the near IR region. And that is what also in the last few years we have been working on in order to find more of these types of emitters. So there's not only interesting photophysics happening on the nanosecond time scale, that is usually the fluorescence of these clusters. But a few years ago, together with a group of Donatas in Lund, we also looked at ultra-fast processes. And we noticed that this Stokes shift, or the difference between the absorption and emission, actually happens on a really ultra-fast time scale. So after excitation, we see that most of the energy, in this case, it's over 1,000 wave numbers, is dumped within 100 femtoseconds, which is an extremely fast process. And also for this particular cluster, we noticed that there is some quantum beating, meaning that sort of the initial beating is transferred from the excited state to the emissive state, and that persists for a few picoseconds. And if you take a Fourier transform of that beating, you can see that that corresponds to vibrational frequencies in the order of 100 wave numbers, which fits very well with what you would expect from silver-silver bonds. So we have ultra fast processes, we have regular nanosecond lived fluorescence, but we also have even slower processes. So even from the early days, it was known that these silver nanoclusters can have microsecond lived dark states. And one way to use them for imaging applications is, for example, by exciting them with regular, in this particular case for this cluster, a green light. And then a fraction of these clusters will go in the emissive state and will fluoresce at, in this particular case, 630 nanometers. But a small fraction can also end up in a microsecond lived dark state. And then by, for example, waiting, in this particular case, 40 nanoseconds, we can come with a second laser and bring it back from the dark state into the emissive state. And as you can see here, by using near-infrared light, we can pump optically the molecule back from the dark state to the emissive state, and we can have what's called optically activated delayed fluorescence. So we basically optically can activate the molecule from this dark state back to the emissive state. And that would be a kind of nice imaging approach to sort of create background-free images, because in this particular case, the fluorescence is anti-Stokes. It's higher in energy than the readout laser. And that would allow you, for example, to make nice background-free images. Okay, let's move on then. So for a long time, people thought these microsecond lived states were dark, but then around 21, 22, people noticed or also reported the presence of luminescence from these long-lived states. And that you can see here. Here are just some examples of one emitter that has dual emission. This particular case, it has nanosecond fluorescence, but also a microsecond lived red-shifted tail. And there are also other clusters. So in 2022, the group of Stacy Cobb showed that there is also clusters that have only microsecond lived emission. And it turns out they also have usually a very differently looking absorption spectrum. Okay, let's continue. So this was another emitter we have recently studied. This was a green emitter, and you can see here, this is a silver 11 7+ cluster. So in total, it has 4 neutral silver atoms. And in solution, it looks like a regular green emitter with only nanosecond lived emission. But in the solid state, either when it's dried up or in the crystalline state, it turns out that this becomes a dual emitter. So what we can see here on the left is we have our silver 11 7+ cluster in solution. We see the nanosecond emission. And then when the droplet dries out, you see the appearance of this microsecond lived emission. If we then rehydrate the dried up droplet, so we add again water, it reforms the same fluorescence as we saw initially. And we can repeat this process many times, showing that the observed emission is sort of dependent on the hydration level of this particular cluster. Same in the crystalline state. When we did these measurements on single crystals, we actually noticed that the polarization of this red-shifted microsecond lived band is actually polarized perpendicular to the fluorescence. So that's quite intriguing, and that could maybe provide us some information about the origin of the electronic state of this long-lived emission. Okay, so That was a lot about sort of spectroscopic properties of these clusters. Now let's switch gears and talk a little bit about structure. Before 2019, basically there was not much or no real structural information available. And as I told you, this field started in 2004. So that means it took about 15 years before people were finally able to find out how the structure looks like. There was a paper from the people I showed you in the beginning, from Jeff Petty and Robert Dixon, that showed the structure of a green emitter. And at the same year, we also published the crystal structure of a near IR emitter. And here were some examples from the crystals we took, and then some single crystal X-ray diffraction our collaborator Jiro Kondo did in Japan. And that allowed us to solve the structure of this cluster, which turned out to be a silver 16 cluster that was encapsulated by two DNA strands. And you can see here nicely that um, most of the nucleobases will bind to the silver. Some of them don't. For example, this one here in position 5, the T is pointed outwards. And also one of the A's at the end is not really interacting with the cluster. There was a little bit of sort of some unsolved issues in this structure. So there were here two atoms that we were not really sure of what they were. They had um, they showed up in the X-ray diffraction, but they sort of had a lower probability or density than the other silver atoms. So initially we were not really sure what they were. You can also see that these particular atoms are not bound to nucleobases. So we were speculating maybe these silver ions can come off or they're not so strongly bound. So that was a little bit of a mystery. Hence, I have here this question mark. But then a few years later, the group of Stacy Cobb showed actually that these two mystery atoms turned out to be chlorides. And that was quite surprising because during the synthesis, we always try to avoid chloride in the reactions. But it turns out that chloride is a very common impurity in many chemicals, and hence this very elegant mass spec data showed that yes, it matches very well with the compound with two chlorides, and even more elegantly when you add then bromide, an excess of bromide, you can see that these chlorides can come off and can be exchanged with bromides. And if you look at the structure, you can actually see that around the position where the chlorides are situated, that there's some kind of tunnel or access to the solvent environment, so these chlorides can come off and can be exchanged with bromides. Not only can these chloride ligands be exchanged, it turned out in a very recent experiment that we did, where we made isotopically pure clusters, that also the atoms themselves can exchange with each other. And that was quite surprising, I would say. So what we're seeing here is an experiment where we made isotopically pure clusters. We have the 107 version and the 109 version. And then we mixed sort of an equal amount of them together. And then we did mass spec and followed how things evolved in time. So you can see here mass spec recorded at 10 degrees. And initially they are separated, but then over the course of several hours, we can see that they start to exchange atoms with each other and they sort of become homogenized in the end. So here we can see this sort of analyzed in more detail, and we can see how we reach an equilibrium as a function of temperature. So at 10 degrees, it takes about roughly 10 hours, I would say, to homogenize, while of course, if you increase the temperature, this exchange will happen a lot faster. Now, the exact mechanism of how this exchange happens, we are not really sure of. So we proposed several ideas. One of the ideas was maybe through this solvent tunnel where the chlorides can be exchanged, maybe also silver ions can come in and exchange with the cluster. Or alternatively, we know from the crystal structure that these DNA stabilized silver nanoclusters like to form crystals and hence sort of interact with each other. So maybe they can form transient dimers in solution, and when they sort of dimerize in solution, maybe at that time point they can also exchange atoms with each other. But understanding this, yeah, might be an interesting avenue in the future to look into. Very recently, with the group of Kirsten, we also managed for the first time to determine the structure of this silver nanocluster in solution. That was done using pair distribution function analysis, so total scattering of this cluster in solution. And for that, as a model, we used the structure from the crystalline state, and then some refinement was done to the PDF that was determined. And then you could actually show that the structure we get in solution is roughly similar as the one in the crystal state. There are some additional rotational and displacement distortions, as you can see here. So the black dots are the positions of the atoms in the crystal, while the sort of yeah, I don't know how to say, the more vague areas are the refined positions in solution. So that's nice. So that could also open up possibilities to study clusters in solution, especially if maybe some of the properties are dramatically different in solution than in the crystalline state. So for this one, it was rather similar, but as I showed you, for example, for the green emitter earlier, sometimes in the solid state, they can have very different photophysical properties than in solution state. Okay, so once we had this crystal structure, Cecilia, she mutated the position 5. So as you can see here, this position 5 was pointing outwards and was not really interacting with the cluster. So it turned out that you can exchange this position and it does not really affect the photophysical properties that much. So as we can see here on the next slide, here we have the absorption spectra of all the mutants of the 5 position. So we have the 5 position with a T, an A, a C, a G, and X, which is in a basic position, meaning no nucleobase. And so the main absorption looks very identical. And then there are minor shifts in the fluorescence, but overall, this indicates, as you can also see here from then the structure determined from single crystal X-ray diffraction, that the structure is fairly similar. The only thing that is different is how they pack in the crystalline phase. So it turns out that this DNA sequence does not only encode, or there are certain nucleotides in the DNA sequence that encode which cluster is stabilized, but there's also other ones, for example, the T in position 5, that can be used to change crystal packing interactions. And maybe some of them might also not be so relevant. So for example, the A at the end can be removed and we still can form the same emitter. So this information that is encoded in the DNA sequence is actually rather complex, and it can be sort of used at different levels. What I mean with that is certain nucleobases are essential for stabilizing the cluster, where other ones are less essential, but could be, for example, then used for other things like, for example, steering crystal packing interactions, or maybe also using them to attach linkers, if, for example, if we want to use them as fluorophores. Another interesting study was where Cecilia exchanged the G, the guanosine, with the non-natural inosine that has one amino group less. And here we can see that even this minor change of removing one amine function can affect the photophysical properties. In one particular case, in this position 7, removing this amine here leads to the loss of hydrogen bonding interactions and in a decrease of the quantum yield and also a lowering of the fluorescence lifetime. While removing it in position 9 here actually improved the quantum yield and also made the fluorescence lifetime longer. So it just shows you that even some minor modifications can sort of fine-tune the photophysical properties. Now I will come to some very recent results that we only published a few months ago. So very recently, we discovered and got the crystal structure of this very near infrared emitter that emits at 960. It turned out that this sequence stabilizes a silver 28 nanocluster with 2 chlorides. And as you can see here, we have a very good, very nice Stokes shift. We have our classic absorption peak at 260 from the DNA, and then the silver-related transition around 850-ish. And as you can see here, they form really nice green crystals. And so we managed to get the structure from these crystals. And I have to thank here also the group of Leila who donated us some beam time and allowed us to get the crystal structure of this. So we solved the structure together with the group of Jiro Kondo in Japan. And you can see here the structure. It's a very long, it's a 2 nanometer long nanorod of silver with, again, 2 chlorides. It seems to be a recurring theme that these chlorides show up even though we do not add chloride to our reaction synthesis mixture. So how does the structure look like? Well, we have basically 2 edge-sharing octahedra, like you can see here. And then in the middle, we have a bridge that is made out of 2 silver tetrahedra, all linked together into one long rod. And in the middle, we also have 2 silver chlorido ligands. Interestingly is when we do mass spec analysis of these clusters, we do not see the chloride ligands. So that might indicate that either they are labile and can come off during the mass spec measurements, or that when they are crystallized, sort of there is some particular driving force for them to be present. So we decided to make sure that these were chlorides, and we added an excess of chloride, of sodium chloride, to our solution, and then we could see at least the adduct with 1 chlorido ligand, but not really the one with 2. So it might indicate that these 2 chlorides are only sort of preferentially there or stabilized when it's in the solid state. Here we actually took one of the crystals and we did some elemental analysis on it, and we could indeed see that at least in the crystal there were 2 chlorides present. So what are sort of the applications or future directions of this? So at some point, since we can make very bright near infrared emitters, we would like to use these as fluorophores in the near IR region. And yeah, that's sort of our potential goal of applications for these emitters. And we have started already to collaborate with some groups. This is an example of a collaboration with the group of Chris Richards in Kentucky, where we used DNA stabilized silver nanoclusters for measuring blood velocities in the brain of a mouse. And with that, I want to thank all the people that have worked on this in my group. So you can see all of them here. Also some collaborators, Jiro Kondo, who was instrumental in helping us with solving the structure. Then some ultra-fast measurements with the group of Donatas and Lund. We have also a long-time collaborator with Stacy. And as I just showed you, we are trying to develop some applications together with the group of Chris Richards in Kentucky. And I have to, of course, also acknowledge the funding agencies. Thanks for the money. That's essential. And thank you all for your attention.